Okay, good morning, Professor David J. De Los Reyes. Okay, I just wear my t-shirt. It's hot. Okay, so I feel comfortable delivering my lecture. Okay, my topic for this morning will be a continuation of my long video format uh, lecture on AC circuit. Okay, let's proceed for this morning. Okay. This is a long video format lecture. This is AC circuit lesson number 3. And the title of the topic will now be, it's a continuation of lesson number 2. Okay, this will be impedance problem or example of impedance problem. So this will be an application on the concept of impedance. Okay, I will try to give you an example problem. I will try to read the problem. Okay, when connected to a 117 volt 25 hertz source, a choke draws 5 amperes. A choke. See? It draws 5 amperes when the voltage is 117 and the frequency is 25 hertz. Choke meaning it's a coil. An example of a choke will be a ballast for a fluorescent lamp. Okay? A ballast contains a coil of windings, okay? That is just needed to stabilize the current for a fluorescent lamp. So an example of a choke will be a ballast. Okay, I will try to continue the problem. When connected to a 120 volt 60 hertz source, the same choke draws 3 amperes. Meaning when that same choke is connected to a 120 volt 60 hertz source, it draws a 3 ampere current. The current consumption become lesser. Why? Because the frequency goes up, right? So meaning to say the inductance of the choke goes up. Okay, that's why the current should go down. Okay, the problem is determine the resistance and inductance of the choke. The problem is asking for the resistance and inductance of the choke. Okay. If we try to bring out the diagram of the choke, it will be something like this. If we try to place a rectangle thing over here, this is considered to be a choke. You have seen a ballast, right? It is something like a rectangular thing. A ballast will be something like this. It got a coil inside, and the purpose of the ballast is actually to stabilize the current going to the fluorescent lamp. Okay? So, that ballast contains a coil, but whether you like it or not, if it is a coil, there will be some resistance inside. It is not a separate resistance for the choke. It's the characteristic already of the coil. Because whether you like it or not, if there is a coil, there should be a resistance. There is no such thing as no resistance for a choke. There should be a very small resistance. Okay? So for figure number 1, when connected to 117 volts and 25 hertz, it draws 5 amperes. So this is the ballast. If we try to draw the component of the parameters inside, that's why our lesson number 2 is parameters, right? There will be a small resistance and the inductance of the coil. The main characteristic of the choke is that there should be an inductance. The bigger portion of the parameter inside the choke will be an inductance and a very small resistance. Small resistance meaning it could be less than 100 ohms maybe. For figure number 2, if that same choke or coil or ballast Okay? If we try to connect it again to a 120 volt in the frequency 60 Hz, it draws 5 amperes. Okay? The frequency goes up, so of course this XL here actually goes up also. So the current goes down. Okay? And the problem is asking what will be the resistance and inductance of the ballast. So actually our problem is just like a verbal problem under algebra. Okay? You apply the concepts on how to bring out the equation to solve the problem. Oh, that's engineering, right? Okay, let's try to bring out the solution. So the problem is asking what will be the resistance R, small r, and what will be the inductance of the coil. Okay, representation. We let small r to be equal to the resistance, L equal to the inductance. Of course, the resistance should be in ohms, and the inductance should be in Henry. Okay, let's try to bring out the solution. In general, E1 is actually the product of I1 times E1. If we try to consider figure number 1, so this subscript 1 here refers to figure number 1. In general, for AC circuit, the product of the applied voltage or the total voltage applied will be equal to the total current drawn by the circuit multiplied by its impedance. Okay? That's a general formula. That is for AC circuit because this is for AC circuit, right? Because for DC circuit, this E here should be equal to I times simply R for DC circuit. Okay? Meaning to say, the voltage of the source should be equal to the total current times the total parameter of the AC circuit. But for this circuit, I'm just comparing the two. The applied voltage should be equal to the product of the total current times the total resistance of the DC circuit. Okay? But the topic for tonight or for this morning is actually an AC circuit. So we forget the second one. But the variation on the concept are actually the same, right? Meaning the product of the total current times the total impedance, the product of the applied current times the total impedance is actually the applied voltage. That's why under the solution, E1 should be equal to I1 times E1, meaning this 117 volts here should be equal to the product of 5 times this total impedance, that is. E1 is equal to I1 times E1. Okay, let's try to compute for the absolute value of Z1 without the angle or without the direction. We will just take the absolute value of the magnitude. The absolute value of Z1 should be equal to the absolute value of E1 over the absolute value of E1. Okay? We compute C1 from this, right? So it will be E1 over I1, right? We know E1, it is 117. I1 is 5 amperes. Okay? So it should be 117 over 5. So Z1 will be 23.4 ohms. So the value of this will be 23.4 ohms. This one. The total impedance. The total impedance includes the small resistance plus the unknown inductive reactance. Right? So meaning to say on circuit number 1, with 117 and 5 ampere, the total impedance that draws 5 amperes is 23.4 ohms. Okay? We'll need this value later on. Okay? Let's try to compute for the inductive reactance at for figure number 1. Inductive reactance is 2 pi FL, right? This is with the subscript 1, so it refers to the inductive reactance of figure number 1. For figure number 1, the frequency is 25 Hz. The inductance is unknown. So the inductive reactance will be 2 pi times 25 times L. 2 pi times 25 is approximately 157. For the meantime, we do not know the value of L. So we will just express XL1, meaning the inductive reactance of figure number 1, that draws 5 amperes, will be 157 times L. the unit of this will be ohms. Okay? Okay, let's try to bring out the vector diagram of impedance number 1 for circuit number 1. Like what I've said on lesson number 2, impedance is a complex number, okay? It got a real part, it got an imaginary part, right? So it got a vertical component, it got a horizontal component. So there should be a triangle for Z1. So the real part will be the unknown small r. Okay, the vertical component will be XL1. But in terms of the unknown inductor, it will be 157L. We have computed the magnitude of the impedance. It is 23.4 ohms. Meaning, if we try to take the square of this plus the square of this should be equal to the square of 23.4 ohms. That's Pythagoras principle under algebra, right? So actually our solution is actually involves trigonometry, right? So if we try to bring out the first equation that involves small r and the inductance, use Pythagoras principle here. It's algebra, right? So the square of the hypotenuse should be equal to the square of r plus the square of this in terms of L. So 23.4 square equal to the unknown small r quantity square plus 157L quantity square. Computing for r square. Okay, we will transpose this to the left when we rearrange. R square will be 23.4 square minus, okay, 157L quantity square. We call this equation number 1. So for equation number 1, we are now given actually a function that involves r and L, and they should be equal to 0. We call that equation number 1, this one. Okay? We are formulating our own equation on how to solve for the unknown value of small r and L. Okay? That's how we work as a mathematician, or for us to be an engineer maybe later. Okay? Okay, let's go with figure number 2. Again, he is using the same formula. The product of voltage, the applied voltage, should be equal to the total current times the total impedance, considering figure number 2. So this is with the subscript 2, it refers to figure number 2, meaning E2 should be equal to, sorry for this one, it should be all subscript 2. Okay, should be I2 times C2. Okay, E2 is actually 120 volts. I2 will the drawn current is actually 3 amperes. So actually, if we are given the applied voltage in the total current drawn, we could compute for the total impedance that draws 5 amperes. Just the absolute value for the meantime. So the absolute value of C2 will be the absolute value of E2 over I2, and then this should be 120 over 3. 120 over 3 will be 40 ohms. So meaning to say, if we try to bring out the vector diagram of C2, considering these values here, it should be this. Okay? It got still a real part, and that real part is still R, the unknown R. Because our resistance is not affected by frequency. It should still be R. So this R here is same as this one. But this is XL here is different from this one because this is at different frequency. And XL2, actually we could compute for XL2 because for figure number 2, instead of 25 Hz, the frequency is 60 Hz. So actually we could compute for XL2. It should be 2 pi times the frequency 60, okay, times the inductance. The inductance is not changing, okay? The only one changing is the value of XL, because the value of XL depends on the frequency. But the inductance on the first equation is the same inductance as for the second one. So if this is L, I will just still designate this L here, the unknown inductance of the choke. So actually XL2 in terms of L is actually 377L. Okay? That is as a function of the unknown inductance of the choke. So if we try to use again Pythagoras principle, algebra, okay? The square of the hypotenuse, which is 40, equal to the square of r, plus the square of XL2, which is 377L, quantity square. Okay? Pythagoras principle. We derive again the next relation involving the relation of R and L using the vector diagram of pseudo. So 40 square should be equal to R square plus 377 L square. Solving for R square. This R here is same as this one. Okay? That's why I didn't change the designation. So R square will be 40 square minus 377 L square, and that will be equation number 2. So after taking the Pythagoras expansion, again we bring out another relation of R and L, and they should be equal to 0. We call that equation number 2. Okay? So we are now given equation number 1 and number 2 that involves R and L. So this falls under the so-called linear equation that involves two variables. So the solution of this is as a part of college algebra. It should be by substitution or elimination or some other things. Okay? But this is R square and R square. So we equate R square using equation number 1 to the value of R square using equation number 2. Where is equation number 2? This one. Okay? So if we try to equate it, 23.4 quantity square minus 157 L quantity square equal to 40 quantity square minus 377 L square. Okay, we lack space. If you try to simplify this one, what will come out for the value of L will be 0.0946 Henry's, capital letter H. And after taking the value of L, we could either go back to equation number 1 or number 2, and we could compute for R. Okay? We just substitute this value here. Okay? Then to compute for R, we take the square root of both sides, so it will be the square root of this. After substituting the value of L. And what will come out supposed to be for the value of R is 18.08 ohms. Okay? That's it. That's how we work in the electrical engineering, okay? We discuss the concept, we bring out the formula, okay? Then we analyze the problem, then using your knowledge of lower mathematics, formulate your own equation, okay, to bring out the equations that will compute for the unknowns. So actually after using figure number 1, number 2, we formulated equation number 1, and using figure number 2, we formulated equation number 2. They are both linear equations, okay? Solving simultaneously, we could compute for the unknown. So the value of L is 0.0946 Henries, and the value of R is 18.08 ohms. Okay, that's it, guys. An example problem involving the concept of impedance. So actually, if you try to see the solution, it involves a triangle. So actually, it involves our knowledge of trigonometry. Okay? Okay, so for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@proofdavidj.Reyes. If you want to share it, please click share. This is my lesson number 3 under alternating current circuit. Okay, good morning from Los Angeles, Professor David J. Reyes.